Okay, so part 2 here. These are some examples of when we will have to substitute the identities in order to factor. All right, so I have 2 sine squared x plus 3 cosine x minus 3 equals 0. Notice these are not the same like terms, so I'm going to take sine squared x and I'm going to substitute 1 minus cosine squared x. This comes from sine squared x plus cosine squared x is equal to 1. If I subtract cosine squared x, then I have sine squared x plus 3 cosine x minus 3 equals 0. I can't forget to distribute this 2. So this is a 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Then I have to get it into standard form. Negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. And I don't like to try to factor with a negative leader, so I'm just going to take out a negative 1. Basically, when I factor out a negative 1, I'm left with positive or the opposite signs of everything. So this will now be a positive. 3 cosine x will now be a negative, and this will be a plus 1. And what happens is if I go through and divide by a negative 1, I still am left with 0. So this is going to be like a 2x squared minus a 3x plus a 1. 2 times 1 is 2. Factors of positive 2, that give me negative 3. That's a negative 2 and a negative 1. Divide by the leader. That becomes, this will be a x minus 1 and a 2x minus 1. So when I bring that over here, I go back and substitute cosine of x for x. Okay, and then I set each factor equal to 0. Okay, this will be cosine of x equal to a positive 1. This will be a cosine of x equal to a positive 1/2. So being a positive 1, that's going to occur at 0. Positive 1/2 will occur at pi over 3 and 5 pi over 3. So if I just want those solutions between 0 and 2 pi, I would just leave 0 pi over 3 and 5 pi over 3. But if I need to do the equations, then I'll have x is equal to 0 plus 2n pi, which is just 2n pi. Okay, x is going to equal pi over 3 plus 2n pi. And x is going to equal 5 pi over 3 plus 2n pi, where n is an element of the integers. Okay, the next one, it looks like I have 3 secant squared x minus 2 tangent squared x minus 4. I have an option. I can choose one or the other. I know that secant squared x is a 1 plus tangent squared x. Okay, so when I go through and distribute, I have 3 plus 3 tangent squared x minus 2 tangent squared x minus 4 equals 0. Now there's not a whole lot to factor here, so I'm going to just combine my like terms. That's going to give me a 1 tangent squared x, and then a 3 and a negative 4 is a minus 1 equal to 0. So I'm going to add 1 to both sides. I'm going to get tangent squared x is equal to a positive 1. Then I'm going to take the square root. And that's going to give me tangent of x equal to plus or minus 1. So if I think back to tangent, that's a positive 1, negative 1, positive 1, negative 1. Then that's going to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And I can write that equation as x equals pi over 4 plus pi over 2 times n, where n is an element of the integers. Since all of those are 90 degrees apart, or pi over 2. So that one actually didn't have any factoring, but I did have to go through and replace the secant squared so that I had like terms. Okay, example next. It looks like I'm going to replace cosecant. You could choose either one, honestly, and they should both work out to the same solutions. So here I'm going to have cotangent squared x plus 1 plus cotangent squared x minus 7 equals 0. Now I put it in parentheses just to show that I substituted it, but since there's a positive 1 out front, I can just kind of drop those. Cotangent squared x plus 1 plus cotangent squared x minus 7 equals 0. And I want to combine my like terms, so that's a 2 cotangent squared x. And then I have a positive 1 and a negative 7, that's a minus 6 equals 0. So I'll have 2 cotangent squared x is equal to a positive 6. Divide by 2. Cotangent squared x is equal to a 3. When I take the square root of both sides, I get that cotangent of x is equal to plus and minus the square root of 3. Okay, when is cotangent the square root of 3? Well, that's at my pi over 6's. That's when tangent is the square root of 3 over 3. So this is the reciprocal. So I've got pi over 6, 5 pi over 6, I have 7 pi over 6, and 11 pi over 6. And if I want to write equations, the cool thing about tangent and cotangent is that they repeat every pi. So I can do x equals pi over 6 plus n pi, and x equals 5 pi over 6 plus n pi, where n is an element of the integers. I could also, instead of 5 pi over 6, I could do negative pi over 6, and that would be equivalent there. Okay, so your assignment is to do some practice out of the textbook, page 373, 37 through 44.